Hello, my name is Daniel Nenny, and I'm the founder of SemiWiki.com, the open forum for semiconductor professionals. Since going online in 2011, SemiWiki.com has experienced more than 4 million users. If you're not a member of the SemiWiki community, please register as my guest. I hope to see you there. Today's webinar is titled IC Manage Holodeck AWS Marketplace Edition Brings Cloud to the EDA Masses. The speaker today is Shiv Sekund, founder and executive vice president at IC Manage. Shiv has been instrumental in achieving its technology leadership in design and IP management for the past 11 years. Shiv has collaborated with semiconductor leaders such as AMD, Apple, Broadcom, Cypress, Intel, NVIDIA, Samsung, and Xilinx in deploying IC Manage's infrastructure to enable enterprise-wide design methodologies for current and next-generation process nodes. Please submit questions on the Questions tab, and we will respond via email after the webinar. Okay, let's get started. Over to you, Shiv.
Hello and welcome to today's webinar introducing an easier path to cloud computing for EDA applications using the IC Manage Holodeck for AWS Marketplace. Thank you for joining, and for those of you I haven't met already, I'm Shiv Sekund, founder and executive vice president of engineering at IC Manage. In developing Holodeck, we wanted to change everything about the way our customers consume compute and software so that the promise of the cloud could be adopted by as many semiconductor design teams as possible. Today, we're introducing an even easier step that allows anyone with an AWS account to start running Holodeck and the low hourly cost integrated with your monthly AWS bill. Let's first start by identifying some of the barriers to running EDA applications in the cloud. First off, setting up a cloud environment that works like your on-premise workflow can be complicated. Every user that wants access needs to have their account and environment set up by your CAD or IT staff. Secondly, to make your EDA flow work in the cloud, you have to copy up all of your data and keep copying as the data changes so your EDA jobs are not working on old or stale data. This can take days for the first copy, and keeping things subsequently synchronized is also very inefficient and costly. We have to deal with managing costs in the cloud. Typically, your CFO does not want to get surprised by bills coming from idle compute nodes or unused storage of hundreds of terabytes of data for many weeks. We also can't afford our EDA applications to run slower in the cloud. That effectively raises the cost of our EDA licenses and slows down the project schedule instead of speeding it up. And lastly, there are many choices for commercial software to try and solve some of these problems. Choices lead to evaluations, negotiations, and purchasing cycles that lead to delays and inefficiency. So why can't we just copy our data and go? Most everyone doing semiconductor design work is running on shared NFS storage. All the applications, scripts, PDKs, and design data are 100% available to your on-premise infrastructure such that any engineer can use any tool they want anytime they want to. Given that all of these necessary elements are ever-changing and growing every day, and they have many interdependencies, it becomes nearly impossible to identify which data set needs to go to the cloud and when it should be updated. Copying everything to the cloud also results in large bills for cloud storage and consumes large portions of your internet bandwidth. So how do we remove all of these barriers and come up with an easy, low-cost way to get to the cloud? Today, we're introducing IC Manage Holodeck for AWS Marketplace, which reduces the technical and cost barriers that enable broad adoption of cloud computing for EDA applications. The key technical capability behind this is Holodeck's ability to instantly project your EDA environment into AWS without having to waste time and money on copying or storing unused data. So how does the new Marketplace edition change things? By making Holodeck a simple checkbox, we've eliminated the overhead associated with doing detailed evaluations, negotiating contracts, etc. You pay for Holodeck per compute node by the hour through AWS, so there are no POs, invoices, or renewals to slow you down. Since Holodeck creates a projection of your on-premise storage when you start a cloud instance, it instantly looks like your whole world from your on-premise environment is already there and ready for work. But most importantly, no actual data is copied up front, just metadata which only takes a few seconds and will have all the same paths as your on-premise NFS filers. The actual file data is uploaded as your application requests it. The granularity of those requests are on a file extent basis, which means that large files that are only partially read can be transferred for just the bits that are read and not the entire volumes. As a result of this, jobs can start very quickly and we can reduce the cloud storage needs by 90% or more. And there you have it. Holodeck lets you run all of your scripts and applications in the cloud just like on-premise without making any changes. So now that we have covered how to get the cloud up and running quickly with low storage overhead, how do we make efficient use of our cloud compute resources? The key to running thousands to millions of jobs is job scheduling automation that can automatically scale up and scale down compute resources as needed. Holodeck for AWS Marketplace comes integrated with IBM's LSF resource connector that can work in a hybrid mode, controlling the scheduling of jobs on-premise or in the cloud. Just as importantly, the combination of Holodeck and LSF resource connector is the ability to bring additional cloud compute nodes online to handle the required load and then shut them down so that there are no idle nodes running up the cost. Running jobs faster is also a key part of Holodeck. We leverage high-performance NVMe storage in the cloud, which allows us to eliminate the storage slowdowns caused by heavy load on shared NFS filers. To have complete transparency for the end users, Holodeck can also save result files back to your on-premise location so that even if the cloud nodes get shut down on job completion, the results are persistent back on the original NFS filer on-premise rather than chewing up dollars in the cloud. So how does Holodeck get faster runtimes? We have seen some I/O-intensive jobs run more than 2x faster in AWS versus on-premise. As we stated in the last slide, Holodeck relies on readily available NVMe storage for large local caches on cloud compute nodes. This means extremely low latency for reads and writes on every node, and the more nodes you add, the more aggregate performance you get. Shared storage tends to divide its performance across the number of compute nodes. Holodeck actually multiplies it. Holodeck also allows any new data created in the cloud to be written back to on-premise seamlessly, but also subject to filtering so you only get what you want, since most cloud providers charge for data sent back to on-premise. They don't charge you for the upload, but they do charge you for the return. The Holodeck system has been pre-configured for AWS Marketplace with pre-built Linux images that are used in a CloudFormation template, which allows you to get up and running very quickly. There are three main Holodeck components. The Holodeck Gateway is a simple Linux process that runs in your current data center and handles read and write requests from applications running in the cloud. The Holodeck Tracker, which is a primary cache for all data coming from the gateway and any data that needs to be shared amongst compute nodes or written back to your on-premise data center storage. It does not run any user jobs or applications. The Peer Accelerator is a software component that runs on each compute node and caches any data requested by that node and stores any data written as part of a job or an application running. The diagram also shows the other key components to round out the solution. IBM LSF for job scheduling and compute resource ramping up and down, and a connection back to the EDA license manager running on-premise. Let's talk about some real-world Holodeck results. This table was derived from an AWS presentation by Xilinx that shows how they benefited from running long jobs that required access to hundreds of terabytes of data. The results are very impressive. Prime time up and running in a few minutes versus weeks to copy data. Job execution was also much faster due to Holodeck's use of local NVMe for caching, and the total storage needed was only 1% of the on-premise footprint. The key point of Holodeck for AWS Marketplace is that you have easy, low-cost access to all of those benefits. For use cases where we want to run thousands of jobs, we leverage the IBM LSF Resource Connector to allow us to schedule jobs and control the cloud compute instances so that we can see a linear reduction in execution time. This example shows that 50 nodes gives us 50x the throughput with jobs starting in seconds and storage savings of greater than 90%. So to summarize before we show you a demo, let's recap the new and unique capabilities that Holodeck provides. You can connect to any AWS region. This means that remote design centers can connect to local AWS regions. There's no efficiency to be gained by everyone connecting to a single central AWS region. As our examples show, getting jobs up and running is fast, and with a pre-configured AWS setup with LSF, it's a complete end-to-end solution that will have you running jobs in minutes. Cloud storage costs are greatly reduced. This reduction makes the cloud ROI even more favorable so that you can increase your cloud usage over time. Lastly, by eliminating the traditional shared NFS bottlenecks, you get faster performance that can help you achieve your primary goal of getting more done faster in a very cost-effective manner. Now, let's move on to a demo showing how AWS Marketplace can run 2,000 Verilog jobs in a few minutes.
This demo will show how to use the IC Manage Holodeck product and IBM's LSF Job Scheduler to quickly run over 2,000 jobs in the cloud. Before we get to the demo, let's discuss the benefits that Holodeck provides. First, disk storage savings of at least 50% and sometimes over 90%. Second, EDA jobs can run faster in the cloud, especially when running a large number of jobs or jobs with heavy disk I/O. Third, jobs can start in the cloud in minutes without the need to pre-copy any data or tools. On-premise EDA infrastructure typically uses an NFS filer that all compute nodes can see so that any job can run with any data on any server at any time. This has the drawback that as the number of servers or jobs increase, job performance can decrease due to I/O bottlenecks. To efficiently extend the current on-premise infrastructure to the cloud, Holodeck virtualizes NFS filer mount points and projects them into the cloud without copying any actual file data. Holodeck caches NFS data on demand for datasets that can scale into petabytes. It also can project NFS data to any number of clouds or cloud regions instantly, so there's no waiting to start jobs. Here's a diagram of our demo setup. We have the typical EDA tools, PDKs, and design source data on an NFS drive on-premise. The Holodeck Gateway is a service that connects to the NFS mount points and also contains an LFS job scheduling master controller that can run on-premise, but also starts and controls jobs and compute nodes in the cloud. In the Amazon cloud, Holodeck has a tracker database that acts as a global cache for all data that will be used in the cloud, and each compute node has its own local cache that provides read and write caching for each job as it executes. Each compute node will also have an LSF agent that controls job execution. As jobs get scheduled, the LSF utility starts up 50 nodes with the Holodeck Peer Manager software that manages the data needed for each job. The demo starts with no data and no instances running in AWS. We use the AWS console to start up a VPN, 2 compute nodes, and the Holodeck software. We submit 2015 Verilog regression tests to the LSF resource connector on premise. These tests run assembly code on a CPU design. LSF ramps up 50 compute nodes and then starts running the jobs. The job results are then written back to an on-premise NFS for later analysis. After the last jobs finish, the compute nodes are shut down to minimize ongoing costs. First, we open the AWS console page that shows our pre-configured machine types, one for a VPN, one for the Holodeck tracker, and one for the Holodeck VPM nodes that do the actual computation. We select each of the 3 nodes and launch them. And that leads us to our next page where we actually see the jobs getting scheduled and run through LSF. In the top left window of the screen, the Holodeck Gateway running on-premise registers 5 NFS mount points that we need for our jobs to run. That is all the info needed before starting any job. The top middle window shows how much cloud storage the tracker is currently using. This is the only persistent storage needed in the cloud. The top right window shows how much local cache storage is being used for one compute node. This storage uses local NVMe, so there is no extra storage cost for this data, which can be cleared at any time after job execution. The bottom middle screen shows overall job status as we start ramping job execution. Now we get things started by sending 2015 jobs to LSF to run in the cloud. Note that we're using 0 storage in the cloud, in the top middle and top right screens. LSF job status at the bottom middle shows a few jobs starting up and others pending while new compute nodes are brought online, which are shown in the window on the far right. We see that the storage consumption starts to go up, and also we see on-premise NFS file read activity happening in the window on the far left. We see that some jobs have already finished, but we still have a lot of pending jobs waiting for compute nodes that are still in pending state. All 50 nodes are now booting, but we are seeing the initial jobs finish and data is being written back to the on-premise storage in the lower left window. Now we see all the requested compute nodes come online and active jobs shoot up from 2 to 98. Here we'll speed up the execution clock in the interest of time so that we can fast forward. Jobs start finishing up, and we see the number of active hosts ramp back down to 0. And now the idle compute nodes are shutting down. So let's take a look at the results. If we had only one node on premise, these 2,000 plus jobs would take 3.4 hours and use 1.4 gigabytes of NFS storage. In the cloud, we used only 70 megabytes of persistent storage in the tracker's cache, a 95% reduction for even this small test case. Our first job started running in only 8 seconds, and all 2015 jobs ran in 6 minutes 24 seconds, a linear speedup of 50x using 50 compute nodes. Shutdown time for all 50 nodes was about 1.5 minutes.
That concludes our webinar. Thank you again for participating in the SemiWiki webinar series, and have a great day.